So the Lewis dot structure, we have several rules to follow. First of all, we have to count the total valence electrons of all atoms. Second, we determine the central atom, which is in general the atom with the large number of single electrons. In case we have two atoms of the same single electrons, we choose the central that is the least electronegative. Then, after choosing the center atom and the outer, we join the atoms by at least 2 electrons. So we make one bond between each 2 atoms. Then we count the total valence minus the electron used in bonding. We obtain a number remained of electrons. So this electrons remained will be distributed on the outer atoms. Why on the outer atoms? In order to have orbitals completely filled, so they should have 8 electrons maximum. Exception, the hydrogen should have 2 electrons. This is the DeWitt rule. If we have now, after distributing the electrons on the outer atom, if we have excess of electron valence, we have to put it on the central atom in order to have orbitals completely filled. And if we don't have excess of electron remains and the central atom needs more electrons to have orbitals completely filled, so we have to use lone pairs or non-bonding electrons from outer atom and transform them to bonding. Exceptions of the octet rule: some atoms with odd number of electrons, so they are called radicals. In some Lewis representation, we can find, for example, atom with 7 valence electrons. So it has 3 pairs and 1 electron single. This electron single is called the free radical. Okay, so we obtain a free radical molecule, and the free radicals are in general very reactive and unstable. We have also exceptions. Some atoms can have less than the octet. For example, the hydrogen can have 2 electrons, beryllium, Be, can have 4 valence electrons, and aluminum can have 6 valence electron. We have also the boron. The boron can have 6 valence electrons. Pay attention for the exception 3. For atoms which can have expanded octets, for example, when we pass to the 3rd period or higher, we will obtain d orbitals. For example, in the electronic configuration, we have 4s2, 3d10, 4p6. So now we have, in the 3rd period or higher, we have d orbitals that can be used. And these d orbitals allow to expand the rule from 8 valence electrons for block S and P to 18 electrons if we use D. So for example, if you consider PCl5, you have at least 5Cl. So around P, you have at least 5 bonds. So you have 10 electrons. And now you expand the octet, okay? We will see later why we can expand the electronic distribution from 8 to 18. Or in other words, if you find a molecule that has total valence electron, the central atom that has total valence electron greater than 8, so your structure is not incorrect. You can say that you have expanded octet rule because we use the d orbitals. And we will see in the exercises this type of exception. I pass to the example, which is the written of the Lewis structure for CO2. The total number of valence electrons for CO2, we have 6 for carbon, we have 4 for carbon, 6 for oxygen, and for the second oxygen we have 6, so we have 16. The oxygen has 2 single electrons, the carbon has 4 single electrons, so the carbon is the central atom. Step 3, we have to join the bonds at least by 2 electrons. So we have 16 minus 4 used in the bonding. We have 12 in excess. This 12 electrons will be distributed on the outer atoms in order to have complete octet. So in case of CO2, the central, the carbon has 2 bonds around, so we have oxygen and oxygen. 16 minus 4, we have 12. So we distribute 6 electrons on the first carbon, on the first oxygen, and another 6 electrons on the second oxygen. And as you observed, the carbon in the center need more electrons. So we have 2 possibilities. We can transform the 2 lone pairs from the first carbon, or the 2 lone pairs from the second carbon, or we can transfer 1 lone pair from the first and 1 lone pair from the second. So we obtain 2 different structures, O or O triple bond C, single bond O. These 2 structures, according to Lewis, are acceptable since Lewis structure is responsible only for the distribution of the valence electrons. In Lewis structure, we are not interested about the types of bonds. We have another example 3.2 or application 3.2. You can solve this Lewis structures. For example, I will consider HCpO4. The total valence we have is 3 times 1 plus phosphorus 5 plus 4 times 6 for oxygen. So we have in total 32. What is the central atom? The central atom in this case is phosphorus, since the phosphorus has 3 valence electrons. Consider SO3 2-. Pay attention for the Lewis representation for polyatomic ions. The total valence is S6 plus 3 times 6. Since we have 2-, so we add 2-. We have to add 2-. So we have 6 plus 3 times 6 plus 2-, so we have 26 electrons. The sulfur has 2 single electrons since it belongs to group 6, and the same for oxygen. So in this case, the sulfur is the central atom, since the sulfur is less electronegative than the oxygen. Resonance structures. What is the meaning of resonance structures? When we write Lewis structure and we have more than one acceptable structure for a molecule, and the structures differ only in the position of the electrons, they are called the resonance structures. For example, in case of CO2, I said that we have 2 possibilities. We take 2 lone pairs from the first oxygen to the central carbon, or we transform one lone pair from the first oxygen and one lone pair from the second oxygen. So we have two Lewis structures. What is the common between these two structures? The common, first we have the same total valence electrons. Second, we have the same order of atoms. In the first, we have OCO. In the second, we have OCO. This is the common between the two structures, the same total valence electrons and the same order of atoms. What is the difference between these two structures? The difference between these two structures is the distribution of the valence electrons. In the first, we have double bond between O and C and double bond between C and O. In the second, we have triple bond between O and C, and we have single bond between C and O. So the main difference between these two structures is the distribution of the valence electrons. These two structures are called resonance. So the resonance structures are the structures for a molecule of same total valence electron. The structures are of same total valence electrons, the same order of atoms, but they differ in the distribution of the total valence electrons. These structures are called resonance. Consider, for example, S2. The total valence electrons is 6 plus 2 times 6 equal 18. So if we write Lewis structure, we join the OS by 2 electrons, SS by 2 electrons, so we obtain 18 minus 4, we have 40 electrons. We distribute 6 on the first oxygen and 6 on the second sulfur. So 14 minus 6 and minus 6 equal 2 electrons. The 2 electrons remain are distributed on the center. So we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. If we look to the outer atoms, oxygen and sulfur, they have orbitals completely filled. But the central atom, which is the sulfur, has total 6 electrons. So the sulfur needs 2 more electrons. These 2 electrons can be obtained by transforming the lone pair of oxygen, the non-bonding electron of oxygen, to bonding, or it can be obtained from the non-bonding electrons of sulfur. So we have 2 possibilities. Lone pair transformed to bonding, so we obtain O double bond S. And another possibility, we transform the non-bonding pair of sulfur to double bond, so we obtain S double bond S. If we look to these 2 structures, they have the same total valence electrons, 18. They have the same order of atom, O, S, S, O, S, S. What is the difference? They differ in the distribution of the total valence electrons. In the first, we put 4 electrons between O and S. In the second, we put 4 electrons, I mean double bond, between S and S. So these 2 structures are called resonance, and the resonance we use in the resonance structure, we use the double arrow in order to describe the resonance. So resonance structures must have the same connectivity, the same order of atoms. The resonance structures must have the same number of total valence electrons. only the distribution of the valence electrons can change. Consider this example. In the first, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. In the second, the total valence electrons is 2 plus 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So these two structures have the same total valence electrons, but they don't have the same connectivity. In the first, we have H, C, C, OH. In the second, the order is H, C, O, C, H. So these two structures are not resonance structures. The first is the Lewis structure for alcohol. The second is the Lewis structure for another family of organic compounds called ether. So these structures are not resonance. Non-equivalent forms. Consider the example of N2O. The objective of this part is to write all possible structures for a molecule, then to study which is the best. For example, N2O. If N2O has 3 acceptable Lewis structure necessary in the nature, N2O exists in one of these structures. So now we have to write all possible structures, then to choose which is the best one. The total valence electrons for N2O is 2 times 5 plus 6 equal 16 electrons. And the central in this case is nitrogen. So we join the atoms NN by 2 electrons and NO by 2 electrons. So we have 16 minus 4 equal 12 electrons remain. The 12 electrons remain. 6 are distributed on the first nitrogen outer in order to have the octet or the orbital completely filled. And on the second, also we use 6 electrons added in order to have orbitals completely filled. So in this figure, we have 6, 8, 10, 12, 14, 16. So we distributed the total valence 16 electrons. But if we look to the central atom, we observe that the nitrogen has only 4 electrons around. And nitrogen is not the exception. Pay attention, the exceptions are hydrogen, 2 electrons, valence, beryllium, aluminum, and boron. So nitrogen is not an exception. It needs more 4 electrons to have orbitals completely filled. In this case, the 4 electrons could be taken from the first nitrogen, or the 4 electrons could be taken from the outer oxygen, or we have another possibility is to transform 2 non-bonding electrons of nitrogen to bonding and 2 non-bonding electrons of oxygen to bonding. So we have 3 figures. In the first, the 2 lone pairs of oxygen were transformed to bonding. In the third, the 2 non-bonding of nitrogen were transformed to bonding. And in the second, we transform 1 lone pair from the first nitrogen and 1 lone pair from the second oxygen. So we have 3 different structures, 3 acceptable structures. And as you observe, we use the double arrows in order to say that these structures are resonance. But now we have to study which is the best between between these three structures. Pay attention for the question. If they ask us to write Lewis structure, we can write one of the three. But if the question is write the best Lewis, we have to choose the best one. So the objective of the next part is to know which is the best structure. We pass to the formal charge. What is the formal charge? The formal charge is the charge calculated for an atom in a Lewis structure on the basis of equal sharing of bond between electron pairs. Suppose you have a bond between A and B, and you have two electrons between A and B, and these two electrons are called bonding electrons or bonding pair, one bonding pair. From these two electrons, A can take a certain electron density and B can take another part. So A can gain a charge, a formal charge that describes the gaining of the electron density around it, and B at the same time can gain a formal charge that describes the electron density around this atom. This is called the formal charge. The formal charge on atom assumes that the bonding electrons are shared equally. The rule, if I have two electrons between A and B, so we will suppose that A and B will share this electron density equally in order to calculate the formal charge. What is the formal charge of an atom in a molecule? The formal charge is equal to the valence electrons of this atom minus the non-bonding electrons around. The non-bonding electrons are the electrons that are not involved in the bonding, are the lone pairs, for example, minus half bonding electrons. For example, I will consider N2O. I will consider the first nitrogen. The first nitrogen, what is the formal charge? First of all, what is the valence electrons of nitrogen? The nitrogen belongs to group 5, so the nitrogen has 5 valence. What is the non-bonding electrons around nitrogen? We have 3 pairs of non-bonding electrons, so in total we have 6 electrons that are not involved in the bonding. So the number of non-bonding electrons is equal to 6 minus half bonding. How many bonding electrons do we have? We have 2 electrons bonding. Why I use half bonding? Because one of these 2 electrons will belong to nitrogen and the other electron will belong to the second nitrogen. And this is what we assume in the formal charge, that the bonding electrons are shared equally. So I return to the example. What is the formal charge of nitrogen? 5 minus 6 minus 1. 2 over 1 minus 1. So it's equal minus 2, the formal charge. The formal charge of the second nitrogen is equal 5, which is the valence electrons, minus 0, we don't have non-bonding electrons, minus half bonding electrons means minus number of bonds. So 5 minus 0 minus 4 is equal plus 1. The formal charge of the oxygen is 6 the valence electrons, minus 2, the non-bonding electrons, minus 3 bonds, or minus 6 over 2. This is the same. So we have 6 minus 2 minus 3 equal plus 1. By the same way, we calculate the formula charges of all atoms in the second structure. For the first nitrogen, we have 5 minus 4 minus 2, so minus 1, the formal charge. The second nitrogen, 5 minus 0, we don't have non-bonding electrons, minus 4 bonds, so it's equal to plus 1. In the oxygen, we have 6 minus 4, we have 2 lone pairs, minus 2 bonds is equal to 0. In the third structure, we have 5 minus 2 minus 3. So we have 0, 5 minus 0. We don't have lone pairs. We don't have non-bonding electrons. So 5 minus 0 minus 4 bonds. So it's plus 1. And the oxygen is 6 minus 6 electron non-bonding minus 1 bond. So it's equal to minus 1. What did we do? First, we write all possible structures for N2O. Second, in each structure, we calculated the formula charge of all atoms involved. Now, comparing the formula charges, we can know which is the best. What are the rules to follow? First, the most favored structure is the one that has the smallest formal charges. The best structure is when all atoms has formula charge equal to 0. Do we have a structure where all the formal charges are equal to 0? No. Minus 2 plus 1 plus 1 minus 1 plus 1 0 0 plus 1 minus 1. Can we compare these formal charges? Can we know which has the smallest formal charge? For example, plus 1 is greater than 0 and minus 2 is less than minus 1. So the formal charges could not be compared. If rule 1 could not be applied, we pass to rule number 2. Rule number 2 states no formal charge with the same sign on adjacent atoms. Why? Because when we have two atoms close, so we have a bond. So we have difference of electronegativity. So one of these atoms is more electronegative, will have a charge minus, and the second will have a charge plus. So it's impossible that two close atoms have the same charge. We look to the structures. In the first, we have plus 1 and plus 1. So the first is eliminated. In the second, minus plus 0. The second, according to rule number 2, is acceptable. In the third, 0 plus minus, the third also is acceptable. So now, in rule number 1, the smallest formal charges, the best, all 0, could not be used. So we pass to rule 2. In the rule 2, we eliminate the first structure, so we obtain two structures. Now, between these two structures, which is the better, which is the best? So we pass to rule number 3. the negative charge should be on the atom the most electronegative, and this is according to the definition of the electronegativity. The electronegativity is the capacity of atom to attract electrons to itself in a molecule. So the most electronegative atom should have a charge minus. Comparing structure 2 and structure 3, which is more electronegative, oxygen or nitrogen? The rule, the famous rule of Falkland-Kapsch states that oxygen is more electronegative than nitrogen. So the minus formal charge should not be on nitrogen, it should be on oxygen. So the structure number 2 is not the best according to these rules. In the structure number 3, we observe that the minus is on the oxygen, which is the most electronegative. So between these 3 possible structures, the best is the third structure.